Hi, this video is going to cover section 6.3 using a technique called volumes by cylindrical shells. You already know how to use calculus to compute volumes, and it's been pretty flexible. It's not that you have exactly one formula, you have one principle. Right? Take a moment and write down, basically speaking, how do we use calculus to find the volume of a three-dimensional object. So hopefully you remember the idea is that we have this three-dimensional object, but it has cross sections. So we imagine moving through this thing, usually left to right, but possibly bottom to top. And we're keeping track of what is the area of each slice. There's a slice here that has a certain area, there's a slice here that has a certain area. And as we move through, the area probably changes. But volume is going to be the definite integral of this function that measures area of the cross sections. And it's a cross section at each x. Maybe here's the area at 2, here's the area at 5, and we're just going across, integrating this function that is keeping track of all of the different areas as we go. That's the general principle that we have used. Maybe we have disks or washers, maybe it's something else, but you just figure out that area function and integrate it. Now, let's look at a problem that maybe isn't so great with this. Let's imagine that we have the region below y equals 4x minus x squared and above the origin. So that's going to be an upside down parabola like so. This is at 4, 0. And it's this region. So this region in pink is the region R. And let's imagine that we're going to revolve R in a horizontal fashion so that we're actually spinning it around the y-axis. So obviously I'm drawing in 2 dimensions, but imagine that we are spinning this, revolving this around the y-axis. If you know what a bundt cake looks like, that's a little bit like the shape we would have. Now, we could do this using methods we already know, but it would be really complicated. I will walk you through the gist of this. So I'm going to copy this. If you really wanted to, you could do this with the washer method. So what you could do is you could split it up in the middle at x equals 2. And we could imagine, let's spin the left side around, we'll get a certain volume, and then we'll spin the right side around and we'll get a certain volume. Since we're spinning around the y-axis, we would actually have to take this equation, y equals 4x minus x squared, and solve for x. And we'd actually have to get a solution on each side. It is theoretically possible, but really, really ugly, and we might be left with an integral we don't know how to do even after we've set it up. Right? Maybe it would be a lot of hard work and we would still have only the calculator. There should be a better way of doing this. So here's what we're going to do. Instead of imagining flat cross sections as we move through this solid, what if we imagined round cross sections? And instead of moving through the object from left to right, what if we imagine we're moving from inside to outside? So I'm going to paste the picture again. And here's what I want us to do. Let's imagine just this portion here corresponding to a value of x. I actually don't like that I have this green stuff, so let me get rid of that. You may not want to copy everything I am doing because the pictures get a little complicated. So let's imagine we just take this vertical segment here and spin that around. When we spin around that vertical segment, what we're going to generate is a cylinder. Right? We're just taking this particular vertical thing. If we take a vertical segment and spin it around a line that it's parallel to, it basically sweeps out a cylinder. And let's imagine just the lateral surface area of that thing. It is not sweeping out the top or the bottom. Right? We are generating this stuff in gray, but it's not giving us anything on the top or bottom of that cylinder. As we spin it around, it's just creating the sides of the cylinder, which has a certain area. I guess there's sort of a back to it too. So at any given point, we could imagine at a certain x value, the vertical segment there gets spun around and it creates a cylinder. Not a solid cylinder, just imagine the outside. We could take a piece of paper and imagine rolling up that piece of paper, just the paper. The paper has been rolled up into a cylinder. And I could do this at every point, right? At every value of x. Over here is a different value of x. And let's imagine this vertical segment. It's taller and farther away from the y-axis. So when this one gets spun around, right, we're going to get a cylinder like so. We're going to get a bigger one. All right, and this one, let me redo this. Let me try to make it prettier. So we spin around that other one and it creates a bigger cylinder. And again, it just creates the outside of the cylinder. Think of it as a piece of paper that has been rolled up with no top or bottom. And then this stuff here would be the cylinder we get. So what we could kind of imagine is that when we spin this whole thing around, it's really just this sequence of cylinders. There's one really tiny one in the very middle, lining up with the y-axis. And then we're going to imagine we're moving somehow outward from the y-axis, getting bigger and bigger cylinders. This is very hard to visualize in just 2 dimensions. I can show you a video. So here's just a little 1-minute video of a similar graph. You're going to see this spin around, and then you're going to see an attempt to kind of build it one cylinder at a time. The cylinders might not be paper thin, but you have the right idea. So we can imagine breaking up that region, and then individual parts get spun around. Right? So there's a part in the middle, and we're spinning that around. We're creating, in this case, a cylinder that has some thickness, but the idea is individual parts, when we spin them around, create cylindrical pieces. Right, here's the one on the inside, and then here is the one after that. So what you're kind of seeing here, and you're only seeing one side of them, we're spinning them around. We're spinning them halfway around so you can see all of them. We have these half cylinders all lined up. And now you're going to see the second half of each one. Right, so they're building outwards. We can't see all of them at the same time, but we know there are these layers of cylinders inside. And theoretically, the whole thing looks like this shape because there are infinitely many of them. This is the shape we're getting. But we can think of this as just a bunch of really tiny cylinders layered upon each other. So we can still think of this as having slices. We can still think of it as cross-sections in a way. They're not cross-sections as we move from left to right. They're cross-sections as we move from the inside to the outside. And because we created this by spinning around the y-axis, there is a circularity. They are all perfectly round. Every one of these is perfectly a cylinder. So what we're going to do is we're going to find the overall volume by taking the integral of these slices. And really, I mean the area of these slices. same idea. We figure out what function keeps track of all the areas, and we'll integrate that from where the thing starts to where the thing ends. No, I do not want to update. So let's actually do that. And what we have to do here is we have to understand what is the area of any particular shape. So I didn't actually address that here. So I'm going to paste my picture again. Here's my original picture. And let's just imagine we're going to think about what is the cylindrical shell. That's how people often think of this, because it's not really the whole cylinder. It's just the outer part corresponding to X. We're going to spin this around. It creates a cylinder, and we want to know what is the area of the outsides. What is the lateral surface area? The lateral surface area of a cylinder is 2 pi times radius times h. We know that the y-axis is the very middle of this thing, so the radius is just the distance from here to x. Whatever x is, that's measuring the radius. And the height is this height here, which would be f of x, which in this case we know is 4x minus x squared. Maybe I didn't call it that before, but the height is the height of the graph at that point. As we move outwards, the radius gets bigger, and then the height gets bigger for a while and then smaller. So the radius is just tracked by x, and the height is tracked by the function f of x. So the lateral surface area at any given place is 2 times pi times x times 4x minus x squared, which is 8 pi x squared. Let me write this better. 8 pi x squared minus 2 pi x cubed, if we distribute. So we can integrate that. We have a function that is keeping track of area, and we're just going to integrate this for all of the possible values for that radius. The very inside is when x is equal to 0. It begins right here with basically a radius of 0, of a little tiny cylinder right here. The biggest one would be if we spin this part around and we get a radius of 4. So our volume is going to be the definite integral from 0 to 4 of our cylindrical shell area. And we saw in this problem that that was 8 pi x squared minus 2 pi x cubed. Right? So we still need to do this. This one's doable without a calculator, so let's do it. We would have 8/3 pi x to the third minus 1/2 pi x to the fourth. We plug in 4, we get 8/3 pi times 64 minus 1/2 pi times 4 to the fourth is 256. If we plug in 0, we get 0. So now, maybe I regret not using my calculator, but this one's doable. This would be 5/12 pi over 3 minus 128 pi. So that's 5/12 pi over 3 minus, if we multiply this, make a common denominator, that's 384. And so after we do the subtraction, that is 128 pi over 3. Right? And I'll just put a little question mark here. I did this really quickly. This video is not about how to do integrals by hand that are not fun very quickly. It's about understanding this method. Instead of moving left to right, we move inside to outside, and every area looks like the surface area of a cylinder. 2 pi times radius times h. So just some things we want to note here. Your intuition might feel off. For the methods we've already covered, when we are spinning around the y-axis, we would have needed to use y as the variable. When we're spinning around the y-axis, we need y as the variable. When we're spinning around the x-axis, we need x as the variable. And here it's actually flipped. The variable of integration was x, even though we were spinning around this, because x is actually measuring how far are we from the center of the cylinder. So that's going to feel a little bit backwards. You really need to visualize what you're doing. I did not give a technical proof of why this works. I kind of just, appealed to the notion of we find volume by integrating areas. This is just a different way of doing it. But if I did it, what would we do? We would set up an approximation of this volume using basic volumes we know. We'd use a limit of that approximation to turn it into the fully correct value. We probably need to do a little bit of algebra trickery to make it look nice. And then we would observe we have a limit of Riemann sums, which creates a definite integral. And what we did before, we can mimic for anything that is round like this, if we can measure the functions fairly easily. Our specific integrand before looked like that. But don't get caught up on a particular formula. Just imagine the little cylinders, and the area is always 2 pi times the radius of the cylinder times the height of the cylinder. In the example we did before, the radius was literally measured by x. The height was literally measured by 4x minus x squared, but maybe there would be some wrinkles. The pattern is better to understand than the formula. All right, so let's do an example together. Let's suppose S is the region bounded by y equals x minus 2 and y equals x. So I'll draw a little schematic diagram here. One of them looks like so. One of them looks like so. And it is this region. Let's find those intersections. So I'll just do this on the side. They intersect when x minus 2 is the same as x. I'll set it equal to 0 so I can factor. So this intersection occurs when x is equal to -1. This occurs when x equals 2. Okay, now we're going to revolve this around the vertical line x equals 4, which would be somewhere around here. So I'm not going to draw anything, but just imagine we're taking this and we're spinning it around. I'm going to draw one of the cylinders later on. Let's write, but do not evaluate, just to make our life easier. What would be the volume we get? So we notice we have a function of x and we're spinning around a vertical line. Cylindrical shells could be helpful. So let's just imagine some arbitrary x. Right, here is just some x value, and this is the vertical portion corresponding to that x value. And let's imagine what happens when we spin just that segment around the vertical line x equals 4. We're going to get a cylindrical shell. So what would be the area of that cylindrical shell? It would be 2 pi times radius times height. Now let's actually make sense of those. The radius is basically just measuring how far is it from the center here to this edge. The center occurs at x equals 4. The edge occurs at just something called x. So that distance is 4 minus x. Because we're spinning around something at x equals 4, so just subtract the coordinates. Our height would be this vertical distance. That vertical distance would simply be the difference between what we get on the top, which is x, minus what we get on the bottom, which is x squared minus 2. If I had named these with functions, right, here's g of x, here's f of x. That height is just f of x minus g of x. It's measuring the vertical distance between those two graphs. So our area here would be 2 times pi times the radius, which is 4 minus x, times the height, which would look like this after I distribute. Lateral surface area of a cylinder is 2 pi rh. Look at your picture, think about what r is, think about what h is. And then what I said is we'll just set up the integral for volume. So we know we're going to integrate this area function. And just pause for a moment and ask yourself, where does x start for this problem to make sense? And where does x end for this problem to make sense? Before, I think I said something about the radius, but we literally are setting it up in terms of x. X begins at -1 and ends at 2. So the radius would be somewhere between 2 and 5, but the x values we're literally plugging in. If you really wanted to FOIL that out, you could do it by hand. You could also punch it into your calculator. This is one of these things where I'm, again, more concerned with do you understand conceptually how to do it than I'm concerned with which particular answer did you get. All right, so let's just do one last example. And this one I want you to try as much as possible before I show my solution. Suppose R is the first quadrant region bounded by the y-axis, y equals 1 and y equals x squared. And let's imagine we're revolving that about the x-axis. Right, so here we're going to have to switch up the variables. That's my hint. So my hint is maybe we're going to need to change variables, right? And that's actually in the instructions. So first what I want you to do is use the washer method with x as the variable to find the volume of the solid. And then use cylindrical shells with y as the variable to find the volume of the solid. So if you're watching this on your own, hit pause and do as much as you can. All right, so I hope you have tried this. Let me draw a picture here. So I have y equals x squared, y equals 1, and the y-axis. So this is our region. We're taking this region, bounded by y equals x squared, the y-axis, and y equals 1. And I'm the first quadrant one, because I guess there's one on the other side. And we're going to spin this around the x-axis, like so. So if we did washer method, let me make a copy of this so that I can draw on it multiple times. With the washer method, with x as the variable, we would imagine here's some x, here is the portion corresponding to x. Each slice would be a washer, and the area of that slice would be pi times the big radius squared minus pi times the small radius squared. This is getting spun around the x-axis. Here's a point on the x-axis. The distance between the center where we're spinning around and the outermost point, they're exactly 1 unit apart, always 1. So our big radius here is 1. And our small radius is the distance between the x-axis and that point here at x comma x squared. So that vertical distance is x squared. The inner radius is x squared. So here we would have x squared squared. So the area of each slice would be pi minus pi x to the 4th. Using the washer method, the volume would be the integral of that area formula as x goes from 0 to 1. So this would be pi times x minus pi over 5 x to the 5th. If I plug in 1, I get pi minus pi over 5. If I plug in 0, I get 0. And our answer is 4/5 of pi. That's using washer method. But we could also use the method of cylindrical shells if we use y as the variable. So I'm going to paste this again. Now, let's imagine y is the variable. Here is the horizontal portion corresponding to y. And we would get a cylinder when we spin that around. So it's the same spin. In the first version, we were thinking, what does it look like if we spin a vertical segment around? Here we're thinking, what happens when we spin a horizontal segment around? If we fix y and look at this horizontal segment, we get a cylindrical shell when we spin that around. So the area of a cylindrical shell is 2 times pi times radius times height. And here we need to realize that the height is actually measured sideways. We are spinning around the x-axis. So the radius is just how far is the x-axis from this point here at y. So the radius is just the y-coordinate. The height is this horizontal distance, and we need to change our perspective. So this graph on the side, let's write it as x equals square root of y. So right here is the point 0, comma y. Right here is the point root y, comma y. This horizontal distance between them, which is actually the height of the sideways cylinder, is root y minus 0. So the height is root y. So we would have 2 pi times y times root y, which is 2 pi y to the 3/2. So our volume would be the integral of this area function keeping track of the cylindrical slices as y goes from 0 to 1. And this is an easy enough integral to do. We needed to simplify that integrand. So we have that as y to the 3/2. But now, what's our antiderivative? So it would bump up to y to the 5/2. 2 pi times 2/5 to cancel that. And if we plug in 1, we get 2 pi times 2/5 times 1. Powers of 1 are really easy. If we plug in 0, we get 0. And wouldn't you know it, it's the same answer we got before, 4 pi over 5. For this particular example, I'm not saying cylindrical shells is easier, but there are certainly problems where it's far easier. That very first example, for sure. At the very least, you just want to have it as an available tool in case you think you need it. All right, that's the end of this video.